Is it recording now? Okay.
Yeah.
Yeah. Okay. So, good morning, everyone. For probably the last session of this year's summer school, and to all my new audience who were not there in the last session, I'll reintroduce myself shortly. I'm Rishabh Srivastav, uh, final year, well, technically graduating in 2 weeks, student from IIT Madras. I completed my BTech in metallurgical and materials engineering and my dual degree in data science. And along with me, I have my two Horizon cohorts, Amishi and Rohit. So before we start, I'll just like to reiterate the rules that we followed in our last session. Uh, like try to make the session as interactive as possible. That's what I usually prefer than just, speaking one way. So either you can use the chat box for asking doubts, or you can simply like, uh, raise your hand so that we'll unmute you. And I hope that my voice remains audible throughout, unlike yesterday's session. But I mean, it probably will. So yeah, we'll get started now. Coming to the second session of cosmology, exploring the unfolding of the universe. Today, we are going to go a little bit deeper into what cosmology is. While we just covered the basics that you need to do cosmology, we covered the Einstein's field equations and stuff. That was not exactly teaching about universe. That's a theory that is used to try to understand the universe around us. And I'm hoping that you guys remember what cosmology actually means. You remember the difference in cosmology and astronomy, astrophysics, and stuff like that. So yeah, let's continue. You can move to the next slide. Now we need to recap certain stuff before starting, just to freshen up your mind. The most important or the most basic thing that we will use to start this discussion is the cosmological principle, which simply means the universe is both isotropic and homogeneous on a large scale. So just keep this phrase in mind, on a large scale. And yeah, I spent quite a lot of time to explain you all what is meant by the large scale. Does someone remember what scale are we talking about? As in, at what lengths can we fairly say that the universe is isotropic and homogeneous? Yeah, as someone has answered 100 megaparsecs. And I'm hoping that yeah, you guys remember the definition of isotropy and homogeneity. Yeah, but like, yeah, now we'll continue. Mm, you can move to. And the next most important thing to remember is the metric that we are following, assuming the universe is isotropic and homogeneous, which is the FLRW metric. And yeah, you all might be very clear about all the terms that are there in this particular metric. Uh, we did not touch a lot upon scale factor in the previous session, and this is what we are going to do in this session. So yes, you can move to the next slide. A little bit of detail about the contents that we are gonna cover in this session. We'll start with the expanding universe. We'll try to understand what is meant by an expanding universe. That is also the name of our session, the description of our session. And further, we'll try to understand something called as a cosmological redshift. You might have heard about Doppler redshift. Even if you studied GR, you will learn something called as the gravitational redshift. Today, we'll see what is cosmological redshift and how is it different? Is it even different from the gravitational redshift that we know about? Further, we'll move on to something called as the Hubble parameter. And then we'll study the dynamics of the universe using Friedmann's equations. Now comes the most important part and the most interesting part as well, where we'll see what is meant by observational cosmology. Because according to me and most of the people, there's no point in studying science in general, if you cannot really observe what you're studying, and you can observe the universe, but how do you observe and do cosmology on that basis? So I personally find that very interesting. And if time permits, we are not going to extend a lot. We will see some dark stuff, and not in the wrong sense. Yes, you can move on to the next slide. Now, well, we are going to study the expansion of the universe, but before that, we have a photo picture on your screen, and I would like you guys to, yeah, tell me what is it. Okay, I've just started getting some answers. Yes, so they are known as the pillars of creation. Yeah, it is in Eagle Nebula. But then, like, why are we even discussing about pillars of creation? Okay, before that, as a very small detour and a very small question that I want to ask: why are they called as like pillars? Makes sense. It looks like three pillars, but why do we use the word creation there? What is being created? Sure, many new stars are formed there. Is it just the stars that are formed? I mean, technically, yes, it's the stars that are formed. But I heard a very famous line in a movie that I would like to quote here. I don't remember the exact line, but it was like, you know, at the end of the day, at the end of our time, we are all made of stardust. So it's not just the stars. It's like sort of even what we are made of. It is the source of entire creation. Everything that we see around. So it's me who's sitting right here, taking a session. It's you guys who are answering, sitting right there. At some point or another, some part of you was there in this. Probably all the parts of you, all the atoms and stuff that you have in your body was there in was a part of these nebula. Anyways, enough of the detour. But then, why are we interested in this particular session? We are learning about cosmology. Why are we interested in these pillars of creation? Can someone guess? Well, we are not going to spend much time on it. So technically, we are not actually interested in pillars of creation. We are interested in the image that you see on the right hand side, the object through which this picture was taken. Sure, sure, sure. To some extent, it can, but I mean, all these nebulae and stuff, they are not very old when it comes to when you compare it with the age of the universe. So not that. So we are actually interested in the stuff that you see on the right, which is the Hubble Space Telescope. And more than Hubble Space Telescope, we are in this entire session, and even like in general in cosmology, in background cosmology, we will be interested in the first word of that Hubble Space Telescope, which is the Hubble. Hubble is very, very, very important. And now you can move to the next slide. Amish, you can move to the next slide. Yes. So something about the Hubble Space Telescope, something for your information, not really important in the context of what we are going to do today. So I'm not going to spend much time on it. You can just take your time and read about it. And now we start our first topic for today's session, which is the Hubble experiment and something where you will actually understand expanding universe. And I'm hoping most of you might not be seeing the entire heading on your screen. In the expanding universe, you might not be seeing the T in the beginning, the G in the end, isn't it? Or is it just me? Yeah. So do you know the reason for it? Well, it's because when universe expands, there comes a point beyond which you can actually not see anything. So an observable universe is finite. It was just to show you this that you start with seeing stuff, but then as time passes, you start missing out on certain stuff. So we define various horizons in cosmology, and then if things go beyond those horizons, you can no longer see them. And well, let's continue. I'll not take another detour, and we might discuss stuff like this towards the end. You can move to the next slide. Now we are going to see about a very interesting observation. I would say not experiment, because it was not meant to be experimented in that sense. An observation that changed the entire concept of uh, cosmology in a way. An observation that forced theorists to change their theory, to abandon many theories, to modify many theory, and a lot like that. So this is, if I would have to point out a single most important observation with regards to cosmology, it will have to be this. So, uh, I mean, we have a like entire story of stuff that was happening, but for me, it was the 1929's observation that was something which was, the most important. Because before that, there were doubts. People used to discuss about if our universe is static or if it's not static at all. And, what's even the meaning of something being static or something not being static. I mean, it's easier to use the word static and just keep on saying that. But if we are using it in scientific sense, we need to define what that means. So, yeah, in 1908, we have this period luminosity scale, and that helps astronomers to calculate the distance to variable stars from the Earth. Why is this significant? It is because when we say universe is expanding, I mean, space is technically nothing. I mean, as I defined in the previous session, space technically means you take your universe and then you remove everything from it. So we don't really know what it means to have an expansion. Further, that's why all we can see are these, objects that emit light, like the stars. So it was important to measure their distance. Further, in 1912, we could actually measure Doppler shift of spectral lines of certain nebula. And then in 1925, we started noticing from the data that there are red shifts in all these spectral lines. It meant that we are moving away from us. I mean, these objects are moving away from us. And it was further in 1929 that Edwin Hubble, by the way, as you can see, it was in 1925 that we did see stars are moving away. But then I don't know how many of you know about this 1925's Silfers data. And most of you might know about 1929 Hubble's experiment. So why was it that Hubble was given more importance than Silverite? Like, I don't want to go into politics and stuff and who was more powerful and stuff, but from a completely scientific point of view, the reason being that it's not important just to, have an observation. As a cosmologist, it's also your responsibility to devise a theory out of it, to, just try to create a theory that would explain your observation. So it was something like this that Edwin Hubble they did that in a way, changed our entire perspective about cosmology and about our universe. I mean, universe is something that has been observed by lot many people across the world from times immemorable. Like there have been Indians, Greeks, and all that. They have all written stuff. They have this. They have seen the skies. They have pointed the telescopes and everything like that. So astronomy is, in a way, is an ancient science, including cosmology. Everything is an ancient science. We have wondered about all the questions and stuff like that. But then this is something, the 1929 observation was something that had never happened before. Nobody even thought about it. I mean, it makes sense, right? Why would you even think about, I mean, you living on Earth, why would you even think about that? No, your Earth is not like how it was 10 years ago. It has changed, it has expanded, it has contracted. Makes no sense, right? But then it was happening. So yeah, you can move to the next slide. So that's why we'll go a little bit deep into exactly what Edwin Hubble observed. So what he found out was that there are a few nearby galaxies whose velocities were that they were moving towards us. Like for example, most of you might be knowing the fact that our galaxy Milky Way and the next closest galaxy Andromeda is actually going to collide. So when people talk about expanding universe stuff moving away from us, what people miss out on is the fact that, I mean, certain galaxies are not moving away from us. In fact, they are moving towards us. But then he also found out that, and like the majority of galaxies appear to be moving away from our galaxy, I mean, from our galaxy. And most of it just kept on moving away. And that is what may help Hubble interfere that, sorry, infer that like the like almost everything is moving as away as they can. Now, I was expecting a question at this point that if universe is expanding, if everything is moving, away from us, why is why are there certain galaxies that are moving towards us? And if there are certain galaxies that are moving towards us, how do you tell if universe is actually expanding or is it contracting? But then again, since you have not asked this question, I'm not going to answer this. Just keep on searching. It's a very interesting doubt that people have over time. So yeah. Yeah, anyways, as you see, we have like on the right hand side, we have images of Virgo, Ursa Major, and other galaxies, and then how they are moving, how far they are, and how much redshifted they are. The significant redshift has its own significance, which we will sort of understand later. You can change the slide. Yes, so this is like the single most important plot that you would have seen before, and that is like very important to what Hubble observed. When Hubble plotted all these points, what happened was, okay, I see certain messages about the question that I asked. They might be expanding, but let progress, they might be coming near. Oh, well, we'll get into it. We'll get into it later. Just keep on thinking for now. So when what Hubble saw, he did plot it, and the interesting thing that he found was it was not that galaxies are moving away. As like we saw, it was already kind of known by 1925 that galaxies are moving away. It was the relation that Hubble found when he plotted these galaxies with how much distant they were. He found that they are following a linear relation. Well, by the way, at this by this time we know that it does not actually follow a linear relation. The relation that it follows, we'll see that as we move ahead. But yeah, for what Hubble saw, he did notice a linear relation, or the very famous statement being, the farther an object is to us, the faster it is moving away from us, which gives us our Hubble law, for which you can Amishi, you can change the slide. Yes, so this is the very famous Hubble law that we know about. V is equal to H naught into D. Now there are, some very important meaning of all the terms that you see here. Now, when we say velocity, we can easily use the word radial velocity. But then if universe is expanding, the meaning of radial velocity itself changes a little bit. And you might have to, when you think about it deeply, you might start getting more and more confused. So this is the most interesting part I find about Hubble's law, which is the more you think and wonder about Hubble's law, the more surprised and the more confused you get. what exactly is meant by radial velocity. Is it the same as the radial velocity that we observe of an object setting from Earth, or is it something else? Because in an expanding universe, certain objects are also moving towards us. So do we subtract that velocity? And that, is that when we obtain this V? And then D is the proper distance. Now we have not defined proper distance yet. We will define it in future, but yeah. And then, yeah, well, yesterday I told you about two constants. We saw the speed of light in vacuum C, and we saw Newton's gravitational constant G. Other than this, I will say one of the most important constant in cosmology is this H naught, which is the Hubble's constant. Uh, does any one of you know its current value? You can Google it, but please don't. Otherwise, I mean, it won't be fun. I mean, an approximate value of currently known Hubble's constant. There's a reason why I have asked you this question. Okay, okay, okay. Yeah, I'm seeing answers close to 70, and that is true, but it's not 63. I've seen it's close to 70, but there's very interesting. In fact, someone has answered 63, although your units are probably wrong. Uh, but then you see I see two different types of answers. One is very close to 70, more than 70. One is somewhere around like 60 or so. As I would have requested, it's better if we don't go through Wikipedia or like Google it, because it's easy to Google stuff and find out. But I just wanted to, just know about what do you guys already know. Anyways, uh, why is there a difference in these answers is something that we are going to see later. You can move to the next slide. Yes, so we saw something called as a proper distance in the previous slide. So now we need to define it, what that means. Uh, there are two kinds of distance that we actually encounter while doing cosmology. It is because our universe is expanding with it, which we define them as a proper distance and a co-moving distance. I usually like to refer to co-moving distance as co-moving coordinate, because when we saw the FLRW metric, we read something called as, we saw something called as R, the R coordinate. What R coordinate usually does when we do, this coordinate system stuff in our own planet, the R coordinate simply means radial distance between two objects. So that radial distance is actually the distance between two objects as well, isn't it? But then what happens in an expanding universe is something that you need to understand. When I say universe is expanding, I actually mean universe is expanding. It means the space is expanding. So when we define a coordinate system with respect to space, that coordinate systems, it gets attached to the space itself. So when the space is expanding, the coordinate system expands too with it. That is why it is known as co-moving coordinate. It moves along with the expanding space. My point is, uh, can you go to the next slide? Uh, Next slide. I'll come back to this slide later. Huh. My point is, if you see this image that you see on your screen right now, we have Earth and we have another galaxy. I don't know which galaxy it is, and it doesn't matter. Now, distance, if I draw a coordinate system and according to FLRW metric, and then I find this, if I place myself at R equal to 0 or at the origin, so I can say that this galaxy is at R is equal to 200 million light years. Right. And now after some time, the universe has expanded. But then while universe is expanded, the coordinate system has expanded itself. It will be very difficult to do cosmology if we keep on changing the distance to a particular object. Otherwise, what will happen is we won't ever be able to classify that. Okay, first thing is it's difficult to have names of all the all the galaxies that we see. So one of the ways by how we identify certain galaxies is how much far away are they from us. Now, since the universe is expanding, everything is expanding, things are moving away from us. what we do is, I mean, it gets a bit difficult if we, just keep on changing an object's distance from us. So since the universe itself is expanding and our coordinate system is itself expanding, the value of r remains the same at any point. So even after a certain period of time, the co-moving distance or the coordinate distance, the value of r that we saw in the this thing in the FLRW metric, it remains same. Or in a way, I can say this statement with a guarantee that our distance from this particular galaxy that I am seeing, or our like coordinate distance, is 200 million light years. It has been 200 million light years forever, and it will be 200 million light years forever. This helps us in classifying this particular object. And then in order to do any physics, or in order to do any cosmology in it, in fact, we will have to, I mean, define something, because ultimately it has expanded. So if we just keep on, they say that if we just keep on saying that the coordinate system is how it was and it is just expanding, so we will never be able to take into account the fact that universe is expanding. Because if our coordinate is expanding, everything is expanding with that. So it like won't matter at all. But then we do see a physical effect of expansion of universe, which we read about a little bit before, and which we will go a little bit deep into a bit later. That the light that we get from that particular galaxy is a bit redshifted. So how do we take into account that? For that purpose, we define something called as a proper distance. A proper distance. Mishi, you can go back to the previous slide. So for that purpose, yeah, we define proper distance. How are we defining proper distance? Proper distance is defined by uh, we multiply our coordinate distance, which is always constant, with the scale factor. This is the first time when you are seeing scale factor, in actual use. So it is because proper distance will change with time as universe expands. But then since R is not changing, it is the scale factor which keeps on changing. So that is something which will keep into account the fact that during Big Bang, everything was at one point in a way. So that the proper distance, there was no distance sort of between any two objects. So it was at the same point itself. And then at some point in later time, it might be, I mean, the distance might be very, very, very huge. So yeah, just keep in mind this relation is important, and more important than that is the definition of the term proper distance, because proper distance is something which will be used a lot in future. And another important thing that you need to keep in mind is, or if you can note this if you have a pen paper in your hand, is that r is not a function of time, but dp, or the proper distance, is a function of time. It changes with time. It is easier to say, but then if you don't keep in mind it is a function of time, you might find things a bit difficult later on. And then you can switch to the next slide again. And yeah, as you see in this slide, the proper distance to this galaxy, it keeps on changing with time. Now, there is one thing that I want to say, but probably not right now. Okay, I'll go into it a bit later. But for now, just see that from future onwards, I will sort of stop using the word time. I mean, from here, we are seeing that it's 3 billion years ago. The scale factor was 0.8. At current time, the scale factor is 1. That scale factor is 1.2 in 3 billion years in future. But from now on, I will stop using the word time, and there's a reason for it. I will let you know why. Someone has asked the question, is it accurate? Is what accurate? Can you like be more specific? I mean, you can type or speak whatever you want, but yeah, it will be better if you are accurate as well with your question. Otherwise, I won't understand. Uh, I am kind of hoping that you're asking if the data which is written here, that if 3 billion years means scale factor being 0.8, current time means scale factor being 1, and 3 billion years in future means scale factor being 1.2 is accurate. Is that what you're asking? Okay. Yeah. So if you want to determine if that is accurate, all you need to find out, we know that scale factor is a function of time. But what exactly is that function? This is the problem in cosmology that is there, and that is something that we need to solve. And more interestingly, this is a problem that has not been solved yet. Another point that I want to mention here is when this problem is solved like properly, it will be a Nobel winning uh, discovery. What exactly is the scale factor function of? Because there are a lot more things to account for them. Like as we go ahead, you will see. Someone is asking about assignments. Well, let's just focus on the session for now. We'll see about the assignments and stuff later on. Let's just focus on what we are doing right now. You will get whatever whatever you need. Yeah. Anyway, so we'll move on to the next slide now. And now, like the most interesting question: if universe is expanding, what does it mean for us? A very interesting question. Have you guys ever thought about when you read the universe is expanding for the first time? If universe is expanding, are you also expanding? Is it that your height is changing with time, or you are just growing apart? Well, you are growing apart with your friends with time. You are not realizing that, but it's a different issue altogether. Anyways, but then yeah, coming back to physics. So, so I mean, if someone says the space between us is expanding, how do you define the space between us? There's space between every atom of your body, right? The space between every molecule in your body. If that space is expanding, and if you are a combination of all those molecules, you might be expanding too, isn't it? Think about it. When you say the space between things are expanding, it is fine. But then, has someone raised their hands? Sure. I mean, by this definition, the galaxy should be expanding as well. It's my question to you guys. If is it happening? I mean, or are you sure it is not happening? Before reaching a conclusion, just think about it. If someone has raised their hands, you can let them speak.
May I ask a small doubt?
Sure, sure, please.
Yeah, so if our cells are also expanding, like everything is also expanding like that, then does the laws like Hubble's law and all apply to that also? Like how is the difference there?
What's the last part of your question that you said? Could you repeat it? What
Like the
exactly was
laws
your?
that govern the universe, so does that apply to all of the everything? Like even the atomic level, does the law like
Yeah,
some
that
laws
is
cannot be
exactly.
applied, right?
Yeah, yeah, I
So
understood. I understood your question. Yes, yes, yes. So let me speak. No, no, that's the thing to think about. That's what actually I am asking to you guys. I mean, the laws of universe, if we call some certain things laws, it should be applicable everywhere, right? So when we talk about expansion, we do talk about I mean, all the laws should also follow that. So if universe is expanding, everything should expand. I mentioned that people talk about atoms, space between atoms, and if that is expanding or if it isn't. My point, I would just like to say one thing that atoms are usually, I mean, governed by. If you go into like in at subatomic level, then no. But at atomic level, it's mostly governed by electromagnetic force theory, and it has an R in it. So in fact, almost every force that we study about, it has an R in it. That R is changing. You need to keep in mind that. So how are we expanding or are we not expanding? This question is something that I will let you think, and I will come into this towards the end of the session. It won't be a part of the session. We can just discuss it. It is something to think about. I mean, and it's better if you think about it. Everything is most of the force. I mean, the four fundamental forces that we see, at least the two of them that I know about very well, are dependent on R. Follows my inverse R square principle. So if R is changing, that force should change as well. Something to think about because we have said it as a law. But we will move ahead. It is for you to think right now, and we'll discuss this later on if you want, and towards the end. You can move to the next slide. But yes, further here we are dealing with something called as the cosmological redshift. So we'll try to understand expansion a little bit more. I mean, we'll get into the physics of expansion a little bit more. Keep that question that I asked in the previous slide in your mind. What is meant by expanding universe and if we are expanding or not. But again, just we'll look into the reason of expansion now for now. What is meant by cosmological redshift. And I'm just assuming you all know about Doppler redshift and all of you know about may not know about gravitational redshift as such properly, but at least know about Doppler redshift because that's where everything starts. Uh, okay, I'll just assume that you know. You can move to the next slide. And yeah, something very obvious. So what happens in an expanding space is how do we even know that space is expanding? Oh, so someone has asked, how do we know that light reaching us has redshift and not originally red, and how do we determine how much the wavelength has changed? Yes, so I answered this question in the like the last session as well, but I'll answer it. I'll explain it to you again. It's very simple. So when we get a spectra from a particular object, there are certain lines that we identify, like the H alpha line and the H beta line, and there are certain lines in that spectra that we know for sure that okay, these are these lines according to the dips that they show. Now, we also know that the lines that we are observing, at what wavelength should they be present? A spectra is this entire shape of intensity versus wavelength. So what happens is we just notice these lines, and if we see that if these lines have changed their position. So if the light was originally red, even in that case, that particular what will happen is the peak of the spectra that you see, it will be towards the red end, but then the dip, the H alpha line will still be at its position at where it should be because the transition that takes place, the this thing that I think it's the 21 centimeter transition, the 21 centimeter line. It still has to remain at that place because that is the particular wavelength at which the this alpha transition takes place in a hydrogen atom. So we just notice the position of that line, and that is how we know. I hope your doubt is clear. I mean, no matter if an object is red or if an object is blue or if an object is whatever, the position of H alpha will always remain same. And it's not just H alpha, it's like the other lines as well. Someone has asked another question, consider us as microorganism Jurassic period and dinosaurs died in microorganism affected distribution. Like equation is expanding, will not expand in the same for universe, is there quantum level? It seems related to the question that I asked before. We'll get into this a bit later. Not really important for our yeah, and then I'll try to finish it on time. I saw the feedbacks that you guys gave yesterday. It was all fine. Just we had a small issue about our session extending a little bit. So I'll try not to extend today, but if it does, we'll have to because it's more important for people to understand than to just keep reading about everything. Yeah, so as you see on your screen, what happens is just like Doppler redshift or Doppler blue shift. I mean, if you're standing at a station, a very famous example that we all know, if a train is approaching you, you do hear this change in frequency. That is exactly what's happening in this case as well. Since we know that an object is moving away from us, the wavelength of the light that we receive, it stretches a little bit. And that is what we receive, and that is how we know that an object has expanded. And so that is what causes the cosmological redshift. Now, yeah, coming back to a question that was asked in the last class about these elements losing energy. If frequency is changing, they might be losing energy too, right? That was the question someone asked. And then where is that energy going? So yes, as I answered yesterday, that is where this energy is going. The light that reaches us, it has to travel, against that expanding universe, and that is where it loses its energy. Now, yeah, you can switch to the next slide. A little bit of explanation about what I just said. Now, my point is, when we talk about cosmology and the expansion of universe, the single most important term that we have seen and we know till now is the scale factor A, which actually sort of takes into account the expansion. But then for redshift, we have we already know the definition of a redshift, right? I mean, it is the z that we use, and redshift is the ratio of the wavelengths that we observe and the wavelength that is emitted. So how do we relate these two? While I mean, there's a proper proof of the relation. I mean, for now, you can just see that, and you can have some idea about how you can relate between these two. What we do is uh, we see the pulse of light that is coming out from a particular object, and when we receive it, and then we also record the next pulse. When is it coming out, and when are we receiving it? So, and then we try to find out the time taken or the distance. I'm sorry, I used the word time again when I promised I won't, but because time gets a bit more confusing as we go along in an expanding universe. That is why I am not going to use time again, but I'm going to define something here. That is something that I will be using from now on. What happens is as it expands, the ratio of the wavelengths is exactly equal to the ratio of the distance or time, whatever. And that gives us the relation that we see, the relation between redshift and scale factor, which is a by a naught is equal to 1 by 1 plus z. Now, this relation is again very important. It is because, by the way, so what is a naught here? A naught is, we saw scale factor a is a function of time, right? So in cosmology, by convention, we define T naught as the current time. So wherever you see T naught, it will mean the current time. So A naught is equal to A at the current time, which in some books, which is A naught is taken as 1. And we define scale factor to be 1 at the present time. But then in order to be more generic, we'll use A naught in most of the places. Wherever we are not using A naught, I'll let you know. And this is how, yeah, again, we define the relation between scale factor and redshift. Now, what we have is scale factor is something that would have determined at what position a particular galaxy is present. Since we have a relation between scale factor and redshift, instead of saying that this particular galaxy is at scale factor of, let's say, 0.8 or 0.5, we can use the term this galaxy is at the redshift of 2 or redshift of 4, right? Did you understand the last line that I said? Just say yes or no. I'll repeat it. Instead of using scale factor as an alias for distance to a particular galaxy or the coordinate of a particular galaxy, we can also use the term redshift. Now, why are we not using distance and time here? It is because of a simple fact that the further we go back, the farther we go back in distance in our universe, the further we go back in time as well. Again, a prediction of special relativity, because speed of light is constant. So time is no longer personal, stuff that we saw yesterday. So again, the further we go, so if I say that an object is at a distance of, let's say, 5 billion light years, I will also have to say, I can also say it in terms of time, that an object is this much time away from us, or the light takes this much time to reach from that object to us, or 5 billion years. So in order to remove that confusion between distance and time, we don't usually talk about, I mean, because we are, using the 4-dimensional space time here. So we sort of don't really take it. I mean, the sort of distance and time are interrelated. So it will be wrong and it will be confusing if I either use the term distance or use the term time. They both are related. So we use the term redshift in that case because it takes into account both of them. So from further on, we are going to use redshift, or the term that I will use is this particular object X is present at redshift something. Another thing that I want to let you guys know is the range of values that A and Z can take. Now, since A and Z are sort of defined in inverse relation, just focus on the fact that as time passes on, since the universe is expanding, what we say is A is increasing, isn't it? Because that's what it means, that the universe is expanding. But in that also means that in the past, A was less than 1. If I say that A naught is 1, I'll say A is less than 1 or A is less than A naught. But then Z is defined as an inverse relation to it. So for Z, we say that if we look at the farthest object to our like so like to our planet or to our galaxy, these objects, since the relation is inverse, these objects are of values. I mean, they have a higher z value. And another reason why we preferred using z value instead of a value to define, distance or time to a particular object was because when classically when we define an object further away from us, we say the further an object is, the higher the value of its distance coordinate is, isn't it? Now, since scale factor had an inverse relation, the further an object is, the smaller scale factor it will be located at. We call A as scale factor and Z as redshift. Yeah, that is all. So it was more convenient for us to use the term Z than A, because it was weird if I keep on saying that, that galaxy, the Andromeda is this much far away from us, it is at scale factor of 0.83. If something is far away, how can it have a value of a metric which is less than 1? So that is why we use Z. For Z, we say that, okay, it is at redshift of 2. Another thing, yeah, how much does it vary? So our scale factor at the time of Big Bang, this is where I want you guys to answer me. What can be the smallest value of scale factor? Yeah, 0. 0 is the right answer. What can be the highest value of scale factor? Yeah, well, this is where we sort of have to understand one thing. The highest value of scale factor can only be 1. No object can have a scale factor value of more than 1 or more than a naught. Because when we say a naught or 1, we mean of present time, or we mean something, an object which is at Earth. We are at scale factor 1. The farther we see, this value of scale factor is going to reduce. So the scale factor goes from 0 to 1 or 0 from 0 to a naught, if you're not defining a naught as 1. Got it? But now coming to redshift. Now, what value can redshift take? What is the smallest value redshift can take? Redshift as in the value of Z, the value that Z can take. And what is meant by a zero value of Z? I mean, this, yeah, I mean, you can type everything. So the zero value of Z simply means scale factor of the current time, no redshift or, yeah, sure. I mean, physically it means no redshift, but in terms of cosmology, it means that it is at current time or like at the current place. In fact, if I would have to call, say, what is my location or your location, it will be Z equal to 0. We are located at Z equal to 0. If you see clearly, Z is equal to 0 correspond to A is equal to A naught or A is equal to 1. And then what is the highest value that Z can take? I'll not try to say no limit. It is infinity. You can either think about it in infinitely far away objects from us are at infinite redshift, or like they are very, very, very highly redshifted. Or if you just want to simply use this relation that you can see on your screen right now, and if you see at what value will you get A equal to 0, you'll get A equal to 0 only at Z equal to infinity, right? It is never exactly infinity, it tends to infinity. So my point is, what happens is when we are using our coordinate system, we define things in this particular manner. Like I say that a very close object to me is at distance 0 to me. And I say that the furthest object to me is at distance infinity to me, isn't it? Now, this is also what Z takes into account. Z also takes value from 0 to infinity, just like our distance does. So that is why Z helps us, comprehend distance a lot better than scale factor, which only varies from 0 to 1, and that too in reverse relation. So someone is asking how if A is up to 1. Oh, simply when will A be 0? At what value of Z? Just look at the relation and tell me at what value of Z will A be 0? What did it be at Z equal to infinity? You need to keep into mind that this both this scale factor A and Z, they are going in reverse order to each other. I hope that it's clear so that we can move ahead. If you ask it out and if I answer it, if it's clear, let me know. If it's not, just let me know that as well. At the value of Z equal to 0, A will be 1, right? Or 1 or A naught. That is fine. My question is, A will be 0 at Big Bang. At what value of Z will A be 0? Or at what value of Z did Big Bang happen? It happened at Z equal to infinity. Or when you're looking at, the further you're looking at, the more you're looking in your past. So technically, the furthest, if you could really look at it, if there was nothing called as, horizon. So the furthest you could see Big Bang happening. Okay. We can move to the next slide. And now coming to the very famous and very important question, how do we quantify the expansion? We did see that we are using scale factor. Scale factor has properties of expansion. It is the only thing which shows that universe is expanding. But can it be used to quantify expansion? I did sort of go through this in our last session. That how do we quantify the expansion? It is scale factor just tells you that, at a particular point in time, what exactly is the scale factor? Or if expansion has happened, the state at which you are right now, that is what scale factor tells us. It does not tell us about how the expansion is happening. How fast is it? How slow it is? And, how is it sort of changing or not changing? And I want you, before me going through to that, I want you guys to just think about it. If scale factor only tells you the present state or the state at any point of time of universe, what is it that we can use to actually tell how the expansion has happened? Or if I can change, put an analogous Hubble's constant is you have moved like two-way in future. We have not yet seen what Hubble's constant is, what Hubble is. Just tell me in terms of whatever we have seen till now. All we have seen is the scale factor. If I would, draw an analogous question to the one that I asked in cosmology, in classical physics, your r or your distance is a function of time, but it only tells you your present location. I mean, your location at time t. Now, if someone moves from point A to point B, r will tell you that the value of r at point A and the value of r at point B. But how it moved from A to B, it won't be covered in r, right? So how will we know that how did someone move from point A to point B? The answer to that question will tell you the answer to this question as well. What is something that can be used sort of to quantify the expansion itself and not the value of the scale at a certain point? I did answer this question in the last session. And the Oh, okay. One thing that when I'm asking how do we quantify the expansion, whenever someone asks you to quantify something, you need to tell the mathematical term or the mathematical, not symbol, mathematical definition of something that can be used. We saw various, variables, various constants, various stuff till now, like C, like R, like kappa that we saw, like A and stuff like that, scale factor and stuff like that. So is there any of these terms that we can use to quantify expansion is what I want to know. Or some manipulation that we can do to these terms that can help us quantify expansion. Think. inverse of d. Again, d is a function of time, but d still does not tell you that how the expansion has happened, right? D will only tell you, I mean, D, since D is a function of time, it will only tell you that, okay, at T naught, this was the value of a 1 by D. And at T is equal to some T, this is the value of D. Someone has said D naught by D. D naught by D is simply A, if you see. So that is my point. Scale factor will only tell you that at time T naught, the value of scale factor was E naught. At time, at another T, the value of scale factor is some other value. Yeah, I don't know what someone has answered density. I don't know what density means right now. We have not seen density anywhere yet, so I don't know what that means. Let's think about the question that I asked before in relation to classical physics. If an object is at point A and then at some time it moves to point B, so its distance only tells you that, I mean, all the value of coordinate R only tells you the value at point A and at point B. What is something that will tell you how it moved from point A to point B? What is that quantity? Distance or A? Yeah, exactly. As someone has answered, derivative. It is the first derivative. In the case of classical physics, it is the velocity that tells you how is it has moved, at what speed it has moved. And yeah, nothing else. It's not the distance. Distance only tells you that where the object is present at one point in time. But how is that? How has it moved? Is defined properly by its first derivative. So analogous to that, the same thing will happen. The way why we quantify the expansion will be used by using scale factor, but not the scale factor in itself. We will be using the first derivative of the scale factor. You can move to the next slide. And hence we define something called as the Hubble parameter. You can move to the next slide. And whatever I was saying here, not double derivative. Double derivative tells you acceleration. It tells you how fast, if at all universe is expanding, how fast is it expanding? That is what double derivative will tell you. But single derivative, but firstly, we need to understand how is it expanding. Is it even expanding or not? Is the first question that one needs to answer, right? If it's expanding or not, or if it was expanding and then contracting, then expanding. That is the first question that one needs to ask. If it is expanding fast or if it is expanding slow, if its expansion is increasing or if its expansion is decreasing, that is something that we ask after that. But yeah, as you can see, the scale factor gives us an idea of the size of the universe, but it does not tell us the manner in which it is actually expanding. Yeah, next slide. Yeah, exactly. Yeah, whatever I said. And that is where we need a quantity which defines the time rate of expansion, isn't it? Now, to what will that quantity be? What could that quantity be that will define the time rate of expansion? And then next slide, you can move to the next slide. Sure, sure. Yeah, it is velocity. I was not asking you a question. I was saying. Mish, can move to the next slide. Yeah. And that is where we define something called as a Hubble parameter, H. And yeah, the definition of H is again very important in everything we do in cosmology. By the way, guys, I want to tell you that cosmology is not just whatever we are doing. Whatever we are doing is known as background cosmology. And then there are other stuff in cosmology as we get deep into it. There are various sub domains in cosmology. People study about inflation. They study about future of the universe. They study about early universe and stuff like that. What we are doing is something very basic that you need to know if you want to, do anything particular in cosmology. So yeah, this is not a complete cosmology. That is what this I wanted to tell you. Yeah, so this is what we define. This is how we define H as. Now, interesting point is we could have simply used A dot. Why are we using A dot by A? The point of using a dot by a is to make this not dimensionless, but to remove, since a scale factor is something new that we defined, not something that has always been there when defining an FLRW metric. So while defining another quantity, we try to remove the dimension of scale factor itself. And if you see, now this is my question to you guys. Uh, and please don't Google it. If you are Googling it, there's no point in answering certain questions. I'll tell what dot represents. So, but yeah, again, please don't Google the questions that I asked. Tell whatever you guys are thinking. It's okay if it's wrong. It's good if it's wrong. We'll see what people can, the different perspectives people can have. Oh, so someone asked me what dot represents. So in physics, in general, if you see a vector or even a scalar with a dot in it, a dot always represents a time derivative. So dA by dt will be referred to as a dot. It is true for, it is not just in cosmology, it is true for anything that you do in physics. So velocity v will be called as r dot. And then there is another derivative. We sometimes we write a and then put this apostrophe on it. So what does that apostrophe represent with vectors? It represents a derivative of a particular vector or a scalar with respect to its own this thing, its own parameter. I mean, every vector or a particular scalar can be dependent on some parameter, right? If let's say we have a temperature T, which is a function of x, y, z, that is the coordinates. So if I write a T prime or a T, that apostrophe thing, I mean is I mean the derivative of T with respect to its parameters, or the derivative of T with respect to the x, y, z. But wherever I write dot, dot only means derivative with respect to time. Okay. Yeah, also I need to tell you here that we saw something called as Hubble's constant, and Hubble's constant is the most famous one that we all have known, we all have read about, and we also saw it in that Hubble's law. Uh, so at this point, while we have reached here, my small request to you guys is try to forget Hubble's law. If you keep in mind that and if you stick to that, you might find things confusing in future. Hubble's law was something given by Edwin Hubble in 1929 when we did not know or we did not use much of physics, or we could not observe beyond a certain point. But that Hubble's law is true. It's not wrong. It's like Newton's gravitation. It is true. It is right. But it is only, it has the scope of it being valid is not like infinite. So yeah, Hubble's constant for now, just kind of forget about it and focus on the Hubble parameter. Now, something interesting. I wanted you guys to tell me what is the dimension of Hubble parameter. Don't Google it. Don't Google anything. Please just, I mean, whatever you have the definition right there. Oh, by dimension, I do not mean your 3-dimensional, 4-dimensional stuff like that. Oh, I'm sorry. Whenever someone asks you dimension, they are asking about you might have read about dimension analysis, right? Like or its unit. Yeah, the better term would to ask would be its unit. People do not know dimension. Yeah, as someone has answered, it is per time. That is the best part about this Hubble parameter. It is given as inverse time. Yeah, second inverse or inverse time. Yes, yes, that's what Hubble parameter is. Now, since you know that, now I want to ask you this question: that what do you think Hubble constant is? Is it related to Hubble parameter? Just answer me yes and no. Do you think Hubble constant is anywhere related to Hubble parameter? Okay. So there are people who think yes, and there are people who think no. Do you remember we saw at the one place we saw A and A naught? I think it was in the previous slide only. We saw A and A naught, and here we are seeing H and H naught. Do you remember how A and A naught are related? Does anyone remember? And when I told you about A and A naught, I told you something else as well there. I told you that in cosmology, the T naught, or wherever we use the term naught, we use it to describe that value of that particular quantity at present time. So when I said A naught, I meant it is A. A is the function of time. It is scale factor at time t naught, which is known as a naught. Can you form a similar relation in this case? Hubble parameter and Hubble constant. It is h and h naught. I mean, it is the exact same relation that I have just talked about for A and A naught. Okay, I'm probably not explaining it to you very well, but so what I am saying is Hubble parameter is a function of time. That you guys agree? Hubble parameter h is a function of time. If h is a function of time, if h is varying with time, sure, it is not just dimensional stuff. Just like A was a function of time, A was varying with time, but A naught is the value of A at the present time. Yeah, exactly. As someone has answered, that is how h and h naught is related. H at t naught or the value of h at present time is actually called the Hubble's constant. So it is not that they're entirely unrelated, Hubble parameter and the Hubble's constant. Hubble's constant is the value of Hubble parameter at the present time. Why is it important? Why is h naught important? Then I also told when I said h naught is an important constant. H naught is something whose value are people trying to determine a lot. And Hubble constant is important because we are living in the present world. So we would like to know the value of Hubble parameter at the present time, because the stuff that we are observing right now, it will be, determined by the value of all these parameters at the present time. That is why A naught is important, H naught is important, all the knots are important, because these are all constants. So to know the current age of the universe, I mean, it helps us find the age of the universe. But I just want to tell you that since H naught has inverse time unit, if you find inverse of h naught, it will give you something in terms of years. That is not the age of the universe. That would have been the age of the universe had the universe not being, okay, I won't say not expanding, but if it would have been expanding at a constant rate. But the problem is, as we will see later on, the universe is not expanding at a constant rate. It is a dangerous thing to know about. If it were expanding constantly, then we could have simply done, 1 by h, and we would have found the age of the universe. Because that's what it is, right? Yeah, what is the confusion about? Is there some confusion that is expanding or not? Universe is expanding. I'm saying that the inverse of h, if you find inverse of h, it will give you some answer with units of time. So, I mean, or h naught. But you cannot say that the value of 1 by h naught you get is the age of the universe. It is because the expansion has not been uniform. The expansion has been accelerating, as we'll see in future. So h naught is a constant, but universe is expanding. H naught is the present value of h. H is a function of time, which actually takes into account expansion. It is a dot by a. So how do we quantify expansion? We use Hubble parameter to quantify expansion. That's it. You can move to the next slide. We are past 1 hour. Okay, before we proceed, have you guys understood whatever we have done this far? Because we are going to go in a completely different domain right now. Well, not completely different domain, but something that we have not yet covered, and something that will be a bit different from whatever we have done till now. It won't be a continuation of whatever we have studied before. So I'll give you guys just 1 minute. If any one of you have any doubts, please type or speak, and then we'll start with Friedman's equations. Friedman's equation is a huge topic in itself. So just try to recall everything that we have studied till now about the expansion of the universe, about redshift, about what Hubble parameter means, about what a scale factor means. And just take your time, just go through it once and try to think if there's something that you have not understood. Because if you have not understood that, it will be a bit difficult for you to understand the Friedman equations. Just a minute's time, we'll start Friedman at 12:10. Okay, I'm really glad. And as I'm seeing that there are no doubts, someone is asking the videos are always available on YouTube for reference. It sure is available, but I won't be available in YouTube, or like the people present here, the courts and everyone else, your TAs are not available on YouTube, so doubts might not be asked. Can you recap that scale factor in short ones? A scale factor is defined by A. It simply takes into account that the sizes in expanding universe are not constant. It is changing with time. So it is a scale factor which takes into account the expansion. We still do not know about how we saw that A is a function of T, but we still don't know what exactly is that function. If it's a sinusoidal function, if it's an exponential function, if it's a polynomial function, we have no idea about it. We have just said that it is a function of time because it changes with time. Scale factor only depends upon time and nothing else. Sure. And so basically scale factor is like a scale in a map. It is a scale in a map at one point in time, but if that scale keeps on changing as the universe expands. That is the entire point of introducing something called a scale factor and calling it as a function of time. So imagine a map that you are stretching it, that map with time. And as you stretch it, the scale factor is also, increasing. Just notice what happens when you're using Google Map and you keep on zooming it. You see the scale that you see, it keeps on changing. So that is what is scale factor is. Our universe is expanding, the coordinate is expanding, so scale factor keeps on changing. That's why I say it's a function of time. And that is why how fast is the scale factor changing? So it's like how fast you zoom in on that Google map actually shows, how fast the scale on that map is changing, right? That is exactly what's happening here. So how fast is the universe expanding is only told by how that scale factor is changing with time. So the first derivative of the scale factor. Scale factor remains constant everywhere in the universe. Scale factor is scale factor. It has got nothing to do with first thing, it has got nothing to do with the position in universe. And secondly, the most important thing, the very first thing that we saw in this particular session, very first slide, the very first thing that we saw, do you remember? Is the cosmological principle. So nothing to do about no different positions in universe. They are all equivalent. We are assuming a homogeneous and an isotropic universe. So there's no way to differentiate between different positions in a universe. So yes, the scale factor remains constant everywhere in the universe because everywhere is everywhere. I mean, everywhere is same. So according to the homogeneous and isotropic universe, I am sitting everywhere taking the session. You all guys are sitting everywhere in the universe listening to this and asking these questions. Okay, I'm assuming, but will it account for inflation too? Inflation is something that occurred in early universe, and inflation is something which is separate topic at all. Right now, when we look at background cosmology, what happens is, so to take into account inflation, we need to take into account what exactly is that scale factor function of. We saw that the scale function A is a function of time, but what exactly is that function? That will take into account scale factor, because if inflation happened or not and how did it happen will only be told by how the scale factor changes with time, right? Or the first derivative, or how the Hubble parameter changes with time. What is the function of that h of t, isn't it? So for studying inflation, we need to know that function. And that is exactly the point of research currently in cosmology. How is that expansion happening and what exactly is the function that is there? So we will look a little bit into it if time permits again. So yes, I mean, I was saying that since we are going to start a new topic, I mean, on a different topic, just keep your questions specific to whatever we have studied till now. If your basics have been clear, or if you have understood everything that I have taught, the questions beyond that we'll cover later on, because again, working on the complaints, a little bit of complaints that I received in the last session, I would like to try to finish it on time. I would like not to exceed it. So yeah. You can move to the next slide. We'll go to the Friedman's equations now. Now we are going to stay in this slide for a while. It has, from now on, we are going to have lots of equations. You might be surprised why you did not see many equations today as you did yesterday. Now is the point where we will start seeing lots of equations. So if you guys have your pen paper, you might start noting these equations on if you want, or you can just listen to it. So what happens is now we have our FLRW metric. You remember the recipe that I taught you about yesterday? We have our FLRW metric and we have Einstein's field equations. What we do is when we put that FLRW metric in that field equation, when we put the value of Einstein tensor capital G and the value of stress energy tensor, by the way, that stress energy tensor in our universe, which is homogeneous and anisotropic, consists only of diagonal elements, of which it is since the LHS, which had the Einstein tensor G mu nu, it had only, it was a 4x4 matrix having only diagonal elements similar to the metric tensor that we saw in the last class. Even the RHS will have only those four elements, the four diagonal elements. And the four diagonal elements in case of stress energy tensor will be uh, rho, which accounts for the density of the universe, the matter density of the universe. I would like to not call it matter density for now, just the density of the universe, density of all the stuff that is present in the universe, density of you, me, and everything else, and pressure. How much pressure does that exerts on us? So, do you understand how are we defining stress energy tensor for our universe? It is a 4x4 matrix with all the off diagonal elements as 0, only the diagonal elements being present, of which the first diagonal element is rho, or the density of all the stuff that is present in the universe, and the rest three are pressure, P, which takes into account the pressure exerted by all the stuff that is present in the universe. Let me use the word stuff in double quotes. And when I hope this is clear, when you put both these tensors in Einstein's field equations in GR, the answer, Einstein's field equations are simply differential equations. If you put that into like the definition of T mu nu and G mu nu in that, the result that you obtain after solving is the Friedman's equations. This is the same Friedman, by the way, after whom we have named FLRW metric ka first F. So once this is clear, you can forget about how do we obtain a Friedman equation. This is just to tell you how we obtained it. But once you sort of have an idea, we can forget about it and focus more on these equations itself. Now, this is how the first Friedman equation looks like. First Friedman equation is a very, very, very important equation. Why, you will get to know it later on. So we need to understand every single term of it. First Friedman equation says that our h square, or the Hubble parameters ka square, which is also equal to, just how we defined h as a dot by a ka square, is equal to 8 pi g by 3 rho minus kappa by a square. And I hope you guys remember all these definitions of what is g. G is the Newton's constant here. Rho, what is rho? So rho refers to the density of stuff present in the universe. Minus kappa by a square. Okay, I'll go to the second part of it later on. Now, so rho is density of stuff present in the universe, which is also equal to the sum of all the stuff, sum of densities of all the present in the universe. Let's say if the universe had three objects A, B, and C, right? Let's just say universe had just three objects A, B, and C. So how did this Friedman equation entirely look like? Would have been 8 pi g by 3 rho A plus rho B plus rho C. So it is a sum of all the rhos or all the densities present in the universe. Is the first term clear? Just say yes or no. This is the first term of RHS in the first Friedman equation. Okay. Now coming to the second term. Second term takes into account. Yeah, we'll get into double dot. Just like the dot represented time derivative, double dot represents double time derivative or the second derivative. We'll get into that. We'll get into that. Before that, the second term of the first Friedman equation minus kappa by a square takes into account the curvature, because curvature is also something which is present in the universe. I mean, even if universe is flat, the value of kappa will be 0. But if it's not so, if you're writing a generic equation, it's good to take into account everything. Later on, if we find out that kappa, if kappa takes the value 0 or not. So the kappa here if you guys remember from our last session or the value of kappa that we use in FLRW metric, it does not take only values of -1, +1, and 0. This kappa is the kappa that takes those discrete values of -1, +1, and 0 divided by the radius of curvature. That is kappa. So the kappa here takes value of it can take any value, to be honest. Any positive or negative value, depending upon what the sign will tell you what the curvature is, if it's positively curved or negatively curved. Or well, technically, I thought that it takes only value from 0, -1 to 1, but it does not. Actually, while it is 1 by r squared, depending upon the unit that we are using for radius of curvature, the radius of curvature can have value less than 1, right? Like we can say that radius of curvature at some places 0.2 centimeter. It depends on the units that we are using. If the radius of curvature is 0.2 centimeter, then the value of kappa in that particular unit goes to more than 1. So that is why, or more than or less than -1. So that is why I'll say that it can take any value. Depends upon the units that we're using. By the way, similar thing works for rho as well. Is k a constant and the rho is changing? Yeah, for now, we won't assume anything being constant. We will assume that everything is changing with time. Because and we'll try to see if it is constant or not. But since we're talking about a genetic equation, we'll assume that everything is changing with time. Everything is a function of time. So the rho is also a function of time, or the densities are changing as the universe is expanding, and we also assume that curvature is also changing with time. Because we are just starting now. We are just writing out all the equations that we need to solve to in order to obtain. Now, what we have done in our first Friedman equation is we have written an equation. As I have said all this while, our goal is to find out what exactly, we know that a is a function of t, but what exactly is that function is what we want to find out. That is what will tell us how exactly is that expansion happening. On as someone said about inflation before, that is also what will tell us if inflation happened or not, because it takes into account everything. Now coming to the someone is asking what is triple equal. It is not called triple equal. It is called as that definition. So whenever you are defining something, you write triple equal. So H is defined as A dot by A, right? It is not something that is given from a particular equation or from a particular solution. It is not solved. We have defined H as A dot by A. That is why I have written triple equal there. Understood? Okay, yeah. These things are new to you all. This is how it is done in usually physics. Now, but we need to continue, guys. It's 12:23 already. Coming to the second Friedman equation. In order to describe, a motion in classical physics clearly, there are two things that we need to know. Just knowing the velocity is not enough. As someone said before, we need to know acceleration as well. So just the first derivative do not give us a complete idea about how this thing is happening. Uh, how a motion is happening. We need to know both velocity and acceleration. Just like that, we need to know both the first and second derivative of scale factor in order to understand the expansion completely. Our goal in entire cosmology is to understand expansion, because it will take us back to all the questions that we asked when we started doing cosmology. As where did the universe start from? Where is it leading? How is the expansion happening? That is the entire question. That is what we need to know. That is the goal of cosmology. So technically, the goal of the cosmology is to find what that scale factor equation is. What is that A as a function of t? That is entire cosmology. So that is it comes from the second Friedman equation. Second Friedman equation has both P and rho. Now, as you see here, in order to solve these two Friedman equations, we will need an additional equation. Right, because we have first and second derivatives of A. For that, we use an equation which is which sort of does not come directly from we are studying cosmology here, nothing to do with magnetism. We are not doing electromagnetism. So I don't understand where this confusion is coming from. So please don't get confused. We are doing cosmology here. So fluid equation, if you try to eliminate stuff from your first and second Friedman equation, you will sort of get your fluid equation. Fluid equation, why is fluid equation important? Fluid equation will tell you. Now, what we are doing is we are not focusing on time here again. As I said before, for us, the unit of distance or something is either scale factor A or redshift Z. So if we want to understand, as someone asked before, that if rho is changing or is it constant, so the fluid equation will tell us how the rho is changing if it is changing with scale factor. Here we are just not taking into account how scale factor itself is changing. We are just trying to find a function of rho in terms of scale factor. Or as we will see later on, how we will change the scale factor to redshift itself. But for now, that's what we're trying to find. That is what this differential equation will tell you. I hope you guys all know what differential equations are and you have learned how to solve it, because that is something which you will need to know, which is like very basic to solving Friedman's equation. Anyways, I hope all the terms in all these three equations are clear. Once we have these steps, we'll go on to solve these things. So before proceeding on to solving the first Friedman equation, we will have to solve the fluid equation to actually find out, how it is changing. Because in order to solve the first Friedman equation, since we have A dot at an LHS, we will somehow need A in RHS too, right? Like time is not something that we are solving for. We are solving for A. We are trying to find how A looks like. So if we have A on the RHS, that is when we'll be able to solve this differential equation. That is how DEs are solved. And that is what we'll use fluid equation for. You can move to the next slide. But then we need additional equation, because we have one thing that you know from very basic is that in order to solve for variables, we need as many equations as the number of variables. Now we have an additional variable. We have both P and rho. So somehow we need to do something to, I said there that we are trying in the fluid equation, we are finding rho as a function of time, but it had P as well, which is also a function of time. So we need to find some relation between P and rho in order to solve that equation. Otherwise, we'll have like in one single equation, we'll have two different variables as a function of time or as a function of scale factor, which I'm using as an alias for time scale factor. So we need to define, or not just define, we need to look at the equation of state. Equation of state is something that is not new. That is something that you have been studying right from your childhood. The most basic equation of state that, do you guys remember the most basic equation of state that you study in your 7th class probably? The first equation of state that you study. We all have studied that and we all know that very, very, very clearly. It might not have terms like density or W. It might not have this form that you are seeing right now, but it has a slightly different form, but it has terms like pressure and in a way density or something else. Anyone quickly? First equation of state that we study. Exactly. It is the ideal gas law. PV is equal to nRT. Or you can sort of try to change this and then convert N and V to form rho density. So ideal gas law is the first equation of state that you study. What does equation of state tell you? Equation of state tells you when we define a relation between pressure and density, your equation of state simply tells you what particular object are we talking about. Remember when I said the rho that we see is the sum of the different components that are present in the universe, or as I said, the universe has A, B, and C, three elements. Assuming a universe has three elements, A, B, and C, so that rho is rho A plus rho B plus rho C. So how do we know what A, B, and C's are? That only equation of state will tell you, because the difference between A, B, and C is that the relation between A, B, and the relation between in their individual pressure of A and rho of A, pressure of B and rho of B, pressure of C and rho of C has different values of this different form of equation of state. And when I say equation of state, I define a new term here, which again becomes very important as we move ahead, which is called the equation of state parameter W. So for ideal gas law, if you manipulate stuff, you will see some constants appearing in this relation. That constant can be called as W, which will be called as equation of state parameter. Now, what we will not we not don't need to define it. If we try to find out the equation of state parameter, we will see that for matter it is 0. The matter that we see here is the non-relativistic matter, or the stuff that we are calling matter here moves at a speed very less than the speed of light. It's me and you. I don't move at speed of light, neither do you, isn't it? So we are matter. If you try to find equation of state, if you try to solve it on your own, you will actually see that there comes a term called v by c, v, the velocity by speed of light. So v by v is very small as compared to c. Our velocity is very small compared to the velocity speed of light. So it's almost zero. So that is why we get that the equation of state parameter for non-relativistic matter is zero. Apart from our universe is just formed from two stuff. That is what we'll assume for now, which is matter and radiation. You don't see, I mean, you cannot tell me about seeing any stuff apart from matter and radiation, can you? Tell me something you know about, you see in the universe, which is there apart from matter and radiation, something that you can observe. Is there anything? Repeat the question. My question was, I am saying that our universe is made of matter and radiation, or relativistic matter, non-relativistic matter, and I can call radiation as relativistic matter, or the photons and stuff as relativistic matter. So, what I am saying is, everything that we have in our universe can be quantified, I mean, can be said to be as either matter or radiation. We have nothing apart from matter and radiation in the universe that we can observe. Do you guys agree? Yeah, so that is a fact. Now, if you try to find the equation of state parameter for radiation, you will see it comes out to be 1 by 3. I'll give you a slight hint how you can solve it. If you remember, we define when we study this thing, kinetic theory of gases. Someone said as universe is made of energy and energy take the form of matter and radiation. Yeah, that's what I said. I mean, when I am saying that the rho, by the way, density and energy density and matter density are the same stuff when you talk in terms of relativity. In relativity, they are E is equal to mc square. So mass and energy are related. I can call it mass or I can call it energy. Similarly, I can call it matter density or I can call it energy density. It won't make any difference. So when I say rho, you can assume it density. It could be anything. Anyways, so how do you get this 1 by 3? I can give you a small hint. If you remember when we are studying kinetic theory of gases, people who have studied it, it's there in school itself. You remember something about velocity of gases and something about 1 by 3 q u RMS square, root mean square speed, something of in that sense. Yeah, there's a 3 in it, right? So if you try to solve it, this is where this 1 by 3 comes from. There's a cosmological constant. Someone is saying, what is the cosmological constant? We have not seen cosmological constant, or we do not observe cosmological constant. What is the cosmological constant? I don't know if I see it or not, if I have any observation or stuff like that. All I see is it's either matter, which is there like galaxies and stuff, or radiation, which is something that I am observing, the like, photons and everything. So I don't know what cosmological constant is, or if it is a component of the universe. Yeah, moving ahead, it's 12:30. We'll move ahead. So we have now defined a relation between P and rho. And then we have for P is equal to 0. And for for matter, it is P is equal to 0. And for radiation, it is P is equal to 1 by 3 rho. We will use this as we move ahead. You can shift to the next slide. Yeah. So something about this curve, this is what our universe represents. Uh, Dark matter or our matter, whatever the matter is, and our baryonic matter. This actually like combines all the matter. The baryonic matter plus dark matter is the entire matter which is present. And then we have something called as the radiation. Radiation is not visible here because radiation is not there right now. It's 0.001. It's even less than that. Yeah, it's very less. And then you also see something called as dark energy there, which is something that we don't really observe. So we have not talked about it. And I don't know. We'll see if dark energy actually exists or if it's just a hoax which is being created for something else. I don't know if it actually exists because I have not seen dark energy anywhere. I have not seen anything pertaining to dark energy. All I have seen are matter, including dark matter and baryonic matter. We do observe, guys know how dark matter is observed, right? I mean, it is not directly observable, but we can see. And then we see other stuff like EA, but we have no idea what dark energy is. So for now, whatever I have seen, I will just say that universe is formed of matter and radiation, which according to this pie chart only tells you about the around what 26%, 5%, around 30% of the entire universe. But that 30% of the universe is the fact to me. And it was a fact to everyone till the beginning of 20th century. We are still in 20th century. So that is all we know about that our universe consists of even till late 20th century. That is what we knew. Our universe consists of just matter and radiation. So that is where we will start with. And we have no idea about the 63%. So if I were to draw a pie chart back in early 20th century, I would call it to represent only these two terms. You can move ahead. Amishi, you can move to the next slide. Now, after we have so we solve the fluid equation, the fluid differential equation, and this is what we get. What we did there was we combined, we changed P as P as P is equal to W rho there, and we made some slight shift to the differential equation. The fluid equation looks like this: d rho by rho is equal to -3 1 plus Wi dA by A. And once we solve this differential equation, we obtain the following relation: rho is equal to rho naught A naught by A, 3 into 1 plus W. This is simple differential equation solving. But then now we know how rho, or how the various components present in the universe varies. I'm looking at the chat box as well. And then, as I've said in the last session, please focus on the session. Attendance will automatically be recorded. It was recorded automatically in the last session as well. Questions are fine, but I don't think these stuff like attendance and all these things are important. And yeah, I mean, also, like, if you are here just for attendance, you might not understand really what I am teaching. And then I'm sorry, but you can just feel free to leave if you want. I mean, if you have some other work or things like that, because your attendance might already be recorded by now. Continuing about the study, dark energy radiation is what? I don't know what dark energy is. I have not studied about dark energy is. I'm still in the early 20th century when I have no idea of presence of anything called as dark energy. All I know about is matter and radiation that I can observe till now. So yes. And then yeah, that is how we define rho. Rho is rho naught A naught by A 1 plus omega. Now we know how rho, as someone was asking that if rho is a function of time or a function of scale factor. Yes, it is. And this is the function that we get from a simple fluid equation and the equation of state. Now W, we all know what W is, right? W is the equation of state factor, which varies for which has the value 0 for matter and 1 by 3 for radiation. You can move to the next slide, Amishi. Yes. Now what we are going to do is, now you need to focus very carefully, otherwise you will lose track of what we have done till now. We are doing something very different and something that will not need for now, might need a bit later in future. We are defining something called as critical density. Why are we doing that? As we saw, Amishi, you actually should go back to the slide where we defined Friedman's equations. The first, second, and third. Yes, just stay right here. Now, if you see right here, there's a small problem, and the problem was pointed out by someone in chat as I saw. The small problem is that someone said we were discussing about the value that kappa can take, and we suddenly found out that the value that kappa can take is actually dependent upon what units do we take. Isn't it? We saw that if it's in centimeters, then it can take different values, or even rho has a unit. It has a unit of inverse volume, right? I mean, there's a big problem if we use stuff like this. If we are dependent upon units, what happens is the value that these things can take will change a lot depending upon what data we're using. It causes confusion, a lot of confusion. I might be recording data in some other units, but someone else might be recording data in some other units, and we might be sharing our data. We might be getting different results, but how do we even comprehend those two results? Because we are looking at the same universe. So something that we need to do here is to define dimensionless quantities. Dimensionless quantities are very important, and across physics, even if you people would have done fluid dynamics, they know about various dimensionless quantities that we define there to see if fluid is turbulent or laminar, and there are lots of dimensionless quantities that we define there. Across physics, we define dimensionless quantities because the values of these quantities, since they do not depend on dimensions. By the way, do you know what the meaning of dimensionless quantities? Dimensionless quantities are the quantities which do not have units. So if things that do not have units, it will have the same value, whatever you do. Like for example, Hubble's constant, it has a unit. So as someone was shared when I asked that question for a response from Wikipedia, in Wikipedia the answer was very different. It was 500 million something something. And then whatever we guys have all seen or known about 70s and all that, it was very different. Why did this difference arise? It was because the units were different, and it causes confusion, right? So we need to introduce dimensionless quantities, which are very important. How do we do that? First Friedman equation is very important. It is actually the equation that we need to solve, and we need to find out stuff that we need. We need to find out how A changes with time. All the first Friedman equation has told us is that the scale factor, the change of scale factor is dependent upon two things. First is the contents in the present in the universe, which is present in the first term of this equation, the rho, and the second term of that equation, which is in the curvature. So I would repeat the theoretical statement of the first Friedman equation. It says that the scale factor of the universe, or the rate of change of scale factor, or the expansion of the universe, is dependent upon the contents present in the universe and the curvature of the universe, whatever that may be. This statement is very important. This is what first Friedman equation tells you. Now the next task becomes to sort of find out what these things are. And for that, we will introduce some dimensionless quantities so that the rho and the kappa, that stuff that we saw, they suddenly become dimensionless. And all we have are certain dimensionless constants, or I should not call them constants. Okay, sure. Let's call them constants only, because since they're dimensionless, they won't change. And since you can go, Michigan, you go to the next slide. इसके बाद वाला. Next to this. And I think, and now since we have defined rho in terms of a constant rho naught, rho naught is, by the way, just as we saw all the knots, rho naught is the present value of rho. So, or the value of rho naught at the scale factor of a naught. So now what has we done in this equation is we have separated the value of rho, which was a function of scale factor a or a function of time, into a constant and a itself, right? So when we do dimensionless, the dimensionless quantities that we will get, they won't be a function of time or a function of scale factor, because we have already separated the present value of all these rows and how they vary with the scale factor. You can go back, go to the slide that we were like the slide where we defined the dimensionless quantities. Yes, just stay right there. So we define something called as a critical density, the critical rho, 3 h naught square by 8 pi g. The reason for that, you will know if you do it by your own hands, you will know the reason for that. Once we do that, now we define these dimensionless quantities. We will call it a density parameters, or the capital omega. So capital omega R is rho R by rho critical, and the capital omega M is rho M by rho critical. And please notice that it is capital rho, sorry, it is rho R naught, it is rho C naught. Similarly, it is rho M naught and rho C naught. Why are we using naught? Because these density parameters are only used for, they are not varying with time. They are the current value of density parameters. So if you want to determine the time varying quantity of the density parameter, it will be rho R into that scale factor wala thing. it will, for radiation, it will be rho r into a naught by a ke power 3 into 1. There was 1 plus W radiation, right? W radiation is 1 by 3. So 1 plus 1 by 3. This is something that will come later on, but just keep in mind the definition of what we have done here, defining the density parameters to make it dimensionless. And these are not functions of time. These are constants because we have separated the function of time, which was the scale factor. You can move to the next slide. Now, what happens is in the first Friedman equation, there was an additional term. The additional term defined curvature, right? So we will be a little bit smart, and what we will do here is we will create a term which will look like another parameter, but which will defined as someone is asking the critical density is defined for spatially flat universe. No, not at all. Yeah, please let me complete whatever I am saying. Just like we had density parameters for matter and radiation, what we will do is we will assume that curvature is also a component of the universe. Just like universe is made of matter and radiation, we will assume that the K or the curvature is also something, a quantity that is present in the universe. And so corresponding to that, we will define something called as a curvature density parameter omega K, just like we had omega R and omega N. Please note that this is not something real. Just like we have matter and radiation for real, curvature is not, like curvature is a quantity that we define to account for the curvature in the universe. But we have been smart here, and we have defined a quantity omega K so that we are able to make the first Friedman equation a little bit easy, and we are able to define it in a more simpler way. So we have defined something called the curvature density parameter, which is minus kappa a naught square by h naught square. Please focus on the knots there. It's a naught and h naught. In the second this thing, in the definition of first Friedman equation, in the second term, it had minus k by a square, if you remember. So we have, since we want our density parameters to be dimensionless, we are using omega k instead, like we are using a naught and k naught, or the current value or the constant value, the things which are not dependent upon time. But once we do that, and once we write our Friedman equation in an alternative form, the first Friedman equations, that is what this is what it becomes, as you can see on your like down there. We had h square, but then while defining critical density, we use something called h naught or the Hubble constant. So we have h square by h naught square, or you can shift the h naught square to the other side. It is equal to h square into h naught square into. So the first term, which had all the 8 pi g's and stuff like that, all these constants, they got involved, they got accounted for in the critical density that we defined, and this is how it looks like. We have a summation over omega i's. Now this summation, what is I? I refers to all the components of the universe. What are the components of the universe? There are three components we know as of now, which is matter, radiation. What is the third component that we know of as of now? Quickly. Curvature, as someone said. So the third component that we know as of now, there are three components. So I goes from radiation, matter, and curvature. We have omega. So h square by h naught square is equal to omega r a by a naught minus 3 1 plus omega radiation. Okay, let's not call it omega. I'll call it w only. W radiation plus omega matter a by a naught minus 3 1 plus omega matter w matter plus omega curvature, just like how we have defined it before, a by a naught a square. And in order to get a square there, you can find out what will be the value of W of curvature. Ultimately, we need a term 2 there, isn't it? So you can calculate, it's not that important, you can calculate it. So my point is, for curvature, W takes such a value that A by A naught power becomes minus 2. Just like it the power becomes, if you try to solve, if you put 1/3 in Wi for radiation, the power becomes -4 actually. So for radiation, the term looks like omega r a by a naught ke power -4 plus omega m a by a naught ke power, it's -3 only. For curvature, it is omega curvature a by a naught ke power -2 is what we will get. So this is how the first Friedman equation looks like. Now, but why is this important? Just keep in mind this first Friedman equation in this particular form. We will see how and why did this equation become important, and how does it help us know the understand the expansion of the universe. You can go to the next slide. Okay, something that I want to mention, I won't take much time in this slide. What is WK? I'm requesting you to calculate the value of WK. All we know is the power that A by A naught will take in that case will be -2. Now you can simply write 3, 1 plus W is equal to 2. And you can solve that to find W for curvature. Did you get what I'm trying to say? You know the power. The power should be 2. Because in the definition of first Friedman equation, you saw that the curvature term had 1 by A square there. So you can find WK in that manner. By the way, guys, so we did introduce a constant called as the Hubble constant at the value of h naught. And since we are using h naught very frequently, it is something that is of significant importance that we need to determine. Like the value of which will actually tell us the present value of Hubble constant. I mean, we know the value of Hubble constant, as you guys all said right now. But then we also need to find out where this value comes from. I mean, you can search for Wikipedia, you can search for things like that to find out what the value is. But since we are studying here, we need to find out how did someone calculate that particular value. In order for to see that, we use this extragalactic distance ladder. What does this tell you? How do we calculate value of Hubble constant? This is where the data scientist in me gets very excited. We have data from various sources, and then we try to find use that data and the equation of Hubble constant that we already have, and then try to fit that data and then try to find the values of constant. That is what we do in basic data analysis. What happens here is, so these are various ways by which you are seeing various sources of data that you are seeing in Hubble constant, depending upon the distance to which we want to know. At like 1 kiloparsecs, we have certain stars, certain clusters, and as we just keep on going in the past, or as we keep on increasing our distance, we use stuff at different distances and found different types of different values of Hubble constant. This is not you need not focus a lot on it, but it is sort of important. Do you see the green box at the very rightmost end of it? SN1A. So the green box at the very right of it, the SN1A is something that we will be interested in, the supernovae data. Because if you see, the supernova is actually used at 100 megaparsec scale, which is the scale at which we actually, our assumption of the cosmological principle is actually truly valid. So we'll be interested in that to calculate Hubble constant and other stuff. The Hubble constant, or that relation with which will that will tell us like how the universe expands, and the other density parameters that would define the value of these parameters will tell us about the amount of matter, radiation, and curvature which is present in the current universe. And the next slide will tell us about more important something which is my personal favorite. You can move to the next slide. Observational cosmology. All this while I have said that we have data from all these sources, we fit that data, and we obtain the value of all these constants. But how do we do that? Like, how exactly do we do that? I mean, yeah, sure, we will go through the paper that you mentioned, but we'll do that after the session. It is actually interesting. Observational cosmology. Astronomy and cosmology is nothing if we don't observe it. And now we are seeing what will we do here. This is very important. I know we are close to the end of our time, but like we have quite some stuff left, so we might exceed today as well. And we will have to. I mean, it's better that you guys understand or not. People who are concerned about attendance, I mean, you guys can leave. It's okay at 1. Let's get started with my personal favorite topic of the observational cosmology. And let's see how do we observe cosmology. Amish, you can move to the next slide. Yes, this is something which is very important. How do you observe certain stuff? You know that universe is expanding, but how do you know? Like as we have seen in our first part of our session about red shifts and stuff like that, the only source of us knowing that something is redshifted or the universe has expanded is by seeing certain stuff. But what do we mean when we call as seeing certain stuff? What are we actually seeing? We see the light that is coming from that object, right? So we have a source, it is emitting some light and we are observing some light. So the property of the light, the property of what we are observing and the property of what was emitted will tell us how the universe is expanding. So it is stuff like stuff which is present too far away. The light coming from there is actually the thing that actually explains us how universe is expanding. Isn't it interesting? Even though the space itself is expanding, it is not the space that we can observe directly, but it is the objects that are present in space that are actually telling us at what pace the space is expanding. Or if I were to go a little bit, if I were to extend a little bit, it is the components of the universe that is telling us how the universe is expanding. And I don't mean this in the Friedman equation way. I mean this in the observational way. So here we will define something called as a luminosity distance, which is very important. We can move to the next slide. The definition of luminosity distance will be very similar to what we have done all this while throughout our life. How we have objects of with certain luminosities and we observe their flux, and their flux have inverse R square relation, and then we use that R square to find out that the distance to that particular source. We will do something similar here. It will be a little bit more complex. But for that, we need to define something called as a standard candle. What we are going to do here is we will have some objects at a particular distance, and those objects will emit light and we will observe that light. So there are two factors that we need to take into account: the objects, the light that those objects are emitting or their luminosities, and the light that we are receiving or the flux that we observe, which will be their luminosity divided by 4 pi r square, as we already know from the stuff that we have studied all this while. And the guys that you would have studied, yeah, it's a basic 10th standard experiment. Yes. The difference between flux and luminosity. And that is what we will be using here. But then for defining luminosity, we need to have certain objects. Can we take observations from all the objects? Yes or no? Come on quickly. Like, can we observe any random object and then we can just, find the luminosity, find the flux, and then find whatever we need and see how the universe is expanding? Any object? No, we actually cannot. The reason being that when we are saying, it's very easy for us to say being in a lab that we have a particular value of flux and then we observe a particular value of luminosity, then we observe its flux and then we find out what that is. But the problem is the flux need not be constant. An object that is usually a black body radiation. I mean, sure, one point is not all objects are luminous. We'll go to that later on. That will help us determine, yeah, what objects we are using. But the another factor is there are objects whose luminosities are not constant. The luminosities keep on changing. We cannot use such objects. If I observe today and I use a particular galaxy and I find its flux, I know its luminosity, and I find some value of Hubble constant and all the other constants that are present. And I said, this is how universe is expanding. Someone tomorrow looks at the same object and its luminosity has changed. We usually assume whenever we are doing observational cosmology using your luminosity distance, we usually assume that the luminosity is constant. We assume that luminosity is the standard property of the particular object that we are observing. Hence, we define something called a standard candle. Standard candles are objects for whom the for whom luminosities are constants. They don't change too much. So that's why we need to understand. You need to understand very well what a standard candle is. If you go out and tell to someone that you have no background cosmology, you have studied it in this session, the first question they will ask you is what is meant by standard candle. Okay, guys, mentioning about dark matter and stuff. There's a reason it is called as dark matter because it does not interact. We cannot see it. Since we cannot see it, it simply means that it does not interact with anything apart from gravity. So no, dark matter does not emit light. It does not emit anything. It does not interact with anything in any form. It just interacts gravitationally. But yeah, we'll go there later. First, let's complete the session. You can go to the next slide. Yeah, as I said, we define something called as a luminosity distance, DL. What is a luminosity distance? It's simply, remember how I said flux is equal to L by 4 pi R square, the 10 standard stuff that we know about. So that if we know the luminosity of an object, if we calculate the flux of that object that we are receiving, we can simply find a distance to object, right? Now the problem is we can, and that is what will give us the luminosity distance, and that would be the distance of that object. But there's a small problem when we do that in cosmology. The small problem arises because universe is expanding, so that distance will not remain constant with time. We need to somehow find a way to relate the luminosity distance to r, because r is something that remains constant, like the coordinate distance as universe expands. So what we do is we change the luminosity distance as that is how luminosity distance is related to r as 1 plus z. Z is the redshift. So for an object located at redshift z, uh, the luminosity distance of that object will be defined as 1 plus z into r, dl. And look where we have put triple equals and where we have put double equals. Double equals is what we find out. Triple equal is how we define certain things. So we define luminosity distance as L by 4 pi f, and everything power 1 by 2. Now we have by L, we have all the luminosity of the stuff that we observe. Flux is something that we observe directly. I mean, flux is something that we observe. L is something which is the property of that particular object that we are observing. But what we need is we need two observables. In doing data science, we need that something that we can observe. You can move to the next slide, Amishi. So the DL that we saw, DL was DL into R. Uh, hang on. I don't understand your question. Let's just hang on. Let's just complete this first. So what we do here is DL is 1 plus z into r, right? As we saw in the previous slides last equation. Now that r, what we need is we somehow need to get rid of that r, because all our observables are, we know that a particular object is at redshift z and is emitting a light with luminosity L that we are observing in flux F. That is all we know about. So what we do here is we try to change that R to something that we know about. Or we use the Hubble value of Hubble parameter there, the H by H. This is where we actually use the first Friedman equation, H by H naught. And this is how we define it. Yeah, time is over. I know, but we are extending a little bit because my stuff is incomplete. But yeah, I mean, feel free to leave if you have stuff to do, or if you have something, so you will be given full attendance. And you will have recordings if you want to observe it later on. I'm sorry, it will be it has to be extended a little bit. Because like, yeah, I stopped, in between. I took some time because it's more important for me for that you guys understand rather than me covering, me just speaking and just not letting you guys speak at all. So yeah, I'll continue and just let me know if you guys have doubts or anything. We'll take some extra time. It won't take much time. This is the last topic that we are covering. And yeah, I'm sorry, just a small thing. It's kind of irritating when we are learning about something interesting and these things are mentioned. So like, feel free to do whatever you want and just listen if you have time. Okay, coming to the DLZ relation, we use Hubble parameter and we sort of find the value of R, and this is what we obtain. How we obtain this is a bit complex, but you can read about it in books. But this is the DLZ relation, which is very important. Keep this in mind. So what we have is, if you look at the you know relation between magnitude, we have flux, and we define luminosity distance dl as some relation between flux and L. We will get into stuff like extinction, mu, and all that, but let's just wait. Please, first let's just go along with everyone. So if you know the, and then where was I? Huh. Our input is the magnitudes that we have, all the luminosity distance that we have, and then we relate that to the this equation that you see here. All the omega i's are clear, I hope. The z's are clear, that is there. The w's are clear here. And then now dl is also not something that we directly observe, right? I mean, luminosity distance is not we directly observe. What we directly observe is the flux of that light, or if somehow we can convert that flux to something else. So here we are defining small m and capital M. I hope most of you know what small m and capital M are. It is apparent and absolute magnitude. If you don't know about it, please read about it. And then we define something called as a distance modulus. Why do we define distance modulus mu? We define it because the data that we observe, no, that data is usually given in terms of mu. So we are limited, since we're doing observational cosmology here, we cannot put random theory. We need to be constrained by the observations that are available, or the data that is available by various observations. So what is the stuff that we observe? We will also look into the stuff that we are observing, that we actually observe. The stuff that we observe, it is given in terms of mu or the distance modulus. Now the question that someone asked, do we include extinction while calculating mu? Not in the definition that we have seen here, but when you're actually doing data analysis, there are certain manipulations that you do in mu, and that is where we actually remove all the extension and everything. Because extinction is not something that every data set takes into account for. So that is why it is not said in the usual theory. Also, people who don't understand what extinction is, yeah, please read about it. It's something that is done in data analysis, just in data analysis. But like we'll focus right now on what is happening here. We can like do all that after the session. So now we have an a value of mu which is given in the data, and we have this relation gives you dl. Now dl is a equation given by the upper stuff that you see. In the upper stuff, you are seeing z. So the data that we have of a certain object, we know its distance from us. So we know the z and we know the mu from the data. And apart from z and mu, everything else that you see are constants, isn't it? H naught is a constant, and then capital omegas are constant, and that is what we need to find. That is what cosmology is all about. Cosmology is entirely about trying to find all these constants, trying to find what the value, what values this constant takes, and that is what will tell us. Once we know the value of omega i's, we can find out the value of all the rows. How is it changing with time? Once we know the value of H naught and the value of how rows are changing with time, we can actually find the value of A, and that is what will tell us everything. So this is the basics of cosmology. That is what we need to find. That is how we do observational cosmology. People who do data science, data scientists simply have observables and parameters. We use observables to find parameter. These are our constant parameters that we find. You can move to the next slide. And there is we saw angular luminosity distance. There's another thing called as angular diameter distance. I won't go too much into this because we are not covering this in our session. But then you can read about it. It is another way of finding distance to certain objects using angular diameter distance. You can read about it when the slides are shared with you. Amish, you can move to the next slide. Now, for me as a data scientist doing cosmology, this is my favorite uh, slide. Not exactly my favorite. I have another slide which is even more favorite, but yeah, something that I am really fond of. This is the data that I have plotted. So the data set from where we have obtained this from is the Pantheon plus shoes. It is the name of the data set. And as you saw from that cosmic distance, the distance ladder slide that we are going to use for our cosmology, we are going to use type 1a supernovae data. Can anyone tell me the reason why we use type 1a supernovae and not anything else? I did tell the reason. And why supernovae only? Why not other galaxies or other stars? Sure. Yeah, one reason is standard candles because they have peak luminosities. There are other stuff as well. I mean, as you saw in that slide, there are this thing as well. There's this Cepheids as well and stuff like that. So there are other stand candles as well. But why do we prefer using type 1 supernova data? Actually, someone has given a kind of answer to it because it is old. When we are trying to find the expansion of the universe, we need to go way in past when even the earliest stars might not have been formed. All the stars and stuff that you see, they have been formed in recent universe. But then supernovae are such bright objects that even if they are very, very, very far away, you still see some light coming from it. Light from it is reachable to us. That is why we use supernovae. Supernovae is the brightest object that is present in the universe. And as you can see, even the brightest object, we can only go to as far as a redshift of 2.0. By the way, this is real data. This is not something that we have created or anything. This is from Pantheon data, which was and the recent Pantheon data. This data was captured in 2022. And the plot that you see right now, this is you won't find this plot on internet or anywhere else. This is my plot. I was doing my research on this, so I have made this plot from like real data. We have a distance modulus on the y-axis and redshift on x-axis. And it is a scatter plot. All the points that you see, these points are actually supernovae. No fitting has been done till now. It is just the supernovae that we have plotted. Each circle represents each supernovae. You can see a lot more supernovae in the smaller sections, 0.0 to 0.5, 0.7. But then as we go further away, the number of points reduce because it's simple. No, the further away we look, the less number of supernovae we have. So yeah, this is the data that we will be using. Now we have a distance modulus mu and redshift z. Our goal is to fit this data with a curve given by the theory that we saw before, the integral theory, and then we try to find all the constants, the omegas and the h naughts. Can you go to the next slide? Yes. And now is the time when we all will look into the dark stuff that you all have been mentioning all this while. And I have tried to ignore it all this while, but now is something we will get into this. So before that, I just want to mention that yeah, so the research that I was doing and I recently completed was on dark energy only. So it will be interesting to know. We won't go very deep into dark energy because the research is still on. Since this is a basic session for US, we'll just do the very basic of dark energy. And this is where you might see stuff that people might have been mentioning, in the chat box since very beginning. You can go to the next slide. You can go to the next. The reason why I am introducing dark energy here is because I cannot do data analysis. I mean, the fact of the matter is dark energy is present in our universe. And since the data which I showed you is real, we cannot do data analysis without introducing dark energy. So yes, we have the cosmological constant here. The cosmological constant, as someone actually mentioned, and I'm really sorry that I said that I don't know what dark energies and all, because I don't want to include it then. You were right. Cosmological constant is is the simplest candidate to dark energy. And this is the story of cosmological constant that most of you already know about. I'll just quickly say that in the initial theory of relativity, the field equation, Einstein introduced an additional term which was not there when I showed you it, which was the term that consisted of lambda or the dark energy. The problem was when Einstein solved that field equation, he found a solution which actually showed that universe is not static, it is changing. Did not mean that it is expanding or contracting, but it is not static. No one liked the idea of an unstatic universe then, and Einstein called cosmological constant as his biggest blunder. What he did was he set it as a value of 0 and he removed cosmological constant from all of his equations. But then later on, when Hubble discovered that universe is expanding, and then when it was discovered that the expansion is not uh, uniform, it is acceleratedly expanding, we had to introduce the cosmological constant again. And so Einstein's biggest blunder actually became the biggest fact. This is how some brilliant minds are. The mistakes that they do is actually the biggest truth of this universe that we are living in. So yes, cosmological constant is the simplest candidate of dark energy that we will see in this particular this thing. And by the way, guys, for people who are wondering, this is the very last topic that we are covering, the cosmological constant. Now you can move to the next slide. We won't just do the theory of the story and the history of it, and I won't just excite you with. I am gonna go into equations and stuff as well. Won't take much time, but just that everything that we have seen, it's the same. But how does the introduction of a cosmological constant changes all the equations that we have seen? That is what we will see. Before that, I just want to mention that when the standard most model of cosmology, it's known as the lambda CDM model. What this model simply says that it is the most widely accepted model. It is the standard model. What this model assumes is our universe is formed of matter, which consists of particularly of cold dark matter. CDM refers to cold dark matter, and lambda, which is the cosmological constant. Cosmological constant takes into account dark energy, and lambda takes into account CDM takes into account the dark matter and radiation as well. But radiation primarily consists of CMB, and it is in very small amounts currently, but it is present. So these are the three things that our universe is made up of: matter, radiation, and cosmological constant, which is dark energy. And another assumption of lambda CDM is that our universe is flat. So we have assumed universe is flat. Our value of omega k is 0. Okay. You can move to the next slide. Now the changes, again, we'll go back to Friedman's first equation. Friedman's first equation that we saw, it had only two terms. But then if you include an additional lambda term in Einstein's field equation, and then you solve it, the Friedman's equation takes the following form. It's very simple. It's just that an additional lambda by 3 terms gets added to it. And we will do the same stuff as we did there. We will, just like for curvature, we define omega k, we will define omega lambda. Since lambda is also an additional this for it. Lambda is also an additional component right now. So we will, since lambda is an additional component, we'll define omega lambda as this particular quantity. To make things easier, you can move to the next slide. Once we do that, this is what we get for lambda CDM model. The h by h naught squared, it is the same relation. I have done like two changes to the relation that we saw then. First thing is the a by a naught that you saw there, it has been changed to 1 by z. Please note that a by a naught had minus 3 1 plus wi. I have changed since the relation is inverse, the powers are positive, not negative here. To make things simple, what I have done here is I have written the expanded equation. We have a radiation term, we have a matter term, and we have a cosmological constant term. And 1 plus z, so the general relation is omega I 1 plus z k power 3 into 1 plus wi. Using that relation, can someone tell me what is the value of w for the cosmological constant? Since you do not see any 1 plus z in the omega lambda term, we assume that it is 0, or it is 1 plus z k power 0. So if that is 0, if 3 into 1 plus wi is 0, what value can w take so that this becomes 0? Yes, as people are answering, it is -1. So the equation of state parameter for the cosmological constant is -1. Since cosmological was a theoretical construct that was included, but then when we defined the equation of state parameter, we defined it as the relation between P and rho, or the pressure exerted by a particular object and its density. And since we say here that this W is -1, pressure becomes negative of density in that case. This is exciting now. And all this while we have seen are all the objects, what happens is they all have this gravitational effect where their presence or their density have a positive impact on pressure, or the pressure they exact, they try to contract the universe. That is what gravitational attraction is. But then this is the only component that we found which had a negative equation of state parameter. -1. What does that mean? Have you ever heard about pressure being negative? What does it even mean to have a negative pressure? This is the first time, this was a revolution in physics. This is the first time that we are seeing something that is something with a negative pressure. So if cosmological constant were an actual object, it would have a negative gravitational force. This sounds very weird, but that simply means that instead of attracting, it actually repels. That is what dark energy is all about. Having a negative equation of state parameter means that the pressure exerted by it is negative, or it is it causes the expansion. And now, since you know that universe is expanding acceleratedly, we also it can give us a fair idea of that the cosmological constant is present, you know, like in majority. It is more than the matter that we have. Once we have this relation, we will go to analyzing the data, and then we will find out what values do we get. You can move to the next slide. Now, this is my actually favorite slide. This is the most important slide. Almost every one of you would have seen the pie chart that you see on the right. You've seen this before as well, about the percentages of dark energy, dark matter, curvature, and everything like that. But no one ever asked me, how do we even calculate these percentages? How do we get these percentages? How do we even know how much dark energy is there, how much dark matter is there? Where do we obtain these percentages? No one can, count them by hand, right? So on the left hand side is again a plot that you see. This is how we do it. And yeah, again, I want to mention, you won't find this on internet anywhere. This is again my analysis that I did for my project. For the lambda CDM model, when I fitted this equation with the data that I had with the line, what the values of constants that I obtained, I have written it here. The omega r was at 10 raised to minus 5. These omegas that you see, these omegas are actually the percentages. So radiation is 0.001% as you see in the pie chart. And then similarly, omega r ka value is a 10 raised to my orders of 10 raised to minus 5. Omega m that I got was 0.34 and omega lambda that I got was 0.66. So these are the values that I got from my analysis of the data. I mean, if you see different analysis, you might get slightly different values. It is because the data present in all that. This is pure data science, by the way. This has nothing to do with the reality. How much is it there in reality? Given the data that I had, these are the values of constants that I obtained. Ignore the chi-square for now. Chi-square is something which is done in data analysis. So if you don't know about it, let's not go into that. It has got nothing to do with the session. So yeah, so this is what we knew about it all. This is what we know about it. And this is what the session was all about. This is where we are actually going to end the session, but like stay tuned. Let me complete whatever I want to say. For now, we have solved this equation. We have fitted the equation for the observational stuff, and we have find the values of all the constants. And now once we know all the constants, by the way, I have not mentioned H naught here. H naught is also a constant that I can determine from this data. Once I know all the constants, I can find DL. Once I know the DL, I can find R, or how Hubble parameter varies with Z. Once I know how Hubble parameter varies, I know how the universe is expanding. One observation that I want you guys to make here is, if you see very close to zero or in the current universe, you see that the line is fairly vertical. I mean, if you just zoom in on that zone, no, you will find that it is actually straight. So that is actually what Hubble observed. At that time, back in 1929, he did not have, the instruments that we have right now. So Hubble was not wrong. It's just that Hubble observed only small portion of this data that I am showing you right now. And that has a linear relation. But then if you go into more and more past, the relation does not remain linear anymore. It changes. That is what shows us that the expansion is not uniform. So it is sort of incorrect to say that the further you go, the faster and the space is moving. Expansion is a little more than that. It is acceleratedly expanding. This is what this fit and this plot tells you. So yeah, this is where like we will sort of end all the theory that we have learned about. But wait a minute. You can go to the next slide, the final slide of our session. Now, interesting. This we still know about this very small portion of the universe, but there's this bigger portion that we still don't know about, the dark energy. But why have I said that? I have just told you what cosmological constant is. We know cosmological constant. Einstein has defined it very perfectly, and we have analyzed our data based on that, and we have done everything. But why do we still say that we don't know about dark energy? Is it fair to say that we still don't know about dark energy? We know everything about cosmological constant, by the way. We know how if we know someone's equation of state, we know about that particular object. Since we know equation of state of dark energy, we should know about cosmological constant. We know about cosmological constant. But do we know about dark energy? Is that it? I did mention a lot many times that research is still going on. If we really know about dark energy, then why are we still say that research is still on? What do you mean by physically? Oh, black holes have nothing to do with dark energy. Dark energy is very independent of any stuff that is present. It's okay, not physically observed, being that is not what's important to cosmology, something being physically observable. Something is present that is being there. Like if I find data which pertains to an observation, even though we might not be able to observe it, because it might not be emitting light or something, or it might have the source of it might be something that might not be there in our insight. But we know that cosmological constant ke bare mein we know. Okay, I am giving you a statement that we know everything on cosmological constant, but I'm still saying we don't know about dark energy. You're we assumed a very basic statement that I did not say that we are assuming that, and you just simply assumed it. Someone has said that in terms of physics, I mean, we haven't figured out any proper uh, we figured out any wave particle properties that these follows. Uh, I mean, yeah, sure. The same can be said about dark matter as well if it follows wave particle. And by the way, when you talk about in cosmological scales, no, the wave and particle, it's not. I mean, everything. You know, the dual nature of light and dual nature of everything. Wave and particle cannot be separated. Waves and particles are the same thing. It is just different ways of observing stuff. Matter is a wave, de Broglie wavelength, de Broglie matter waves. So is the particle. So it is not fair to say. We fairly assumed very simply that dark energy is actually represented by the cosmological constant. But my question is it true? Mudit, I'll come to your assumption about k is equal to. That is not something that we assume. I will come to that. But right now, I just said that cosmological constant is represented by dark energy. Sorry, cosmological constant represents dark energy, but is it true? Yes, it is our assumption, but we do not know if it is true. But why? If something, if I have a theory, and if that theory correctly predicts the data that we have, then that theory should be true, right? That is what science is all about. If you have a theory and that fairly represents the data that we see, that theory is true. That theory is the fact. Then what is the problem? We just saw the fit that I showed you. The fit is perfect. It has no issues. Then why do I keep saying that something does not make sense and I have not don't know dark energy yet? Is there something that lambda CDM, the standard lambda CDM model does not cover, does not take into account? Are there some problems with standard lambda CDM? Yes, there are. Someone said in the very beginning of our session about something called as the Hubble tension. This is where it comes about. So we will not go deep into it. I'll just tell you that there's something called as Hubble tension. While the standard lambda CDM model is a very good model because it shows everything that we know about. There's a small problem with Hubble with lambda CDM, or assuming that cosmological constant actually represents dark energy, is that the Hubble constant that we observe through two different data sets, uh, through type 1 is supernova data as we have done, and through cosmic microwave background CMB, both of them gives very different values of Hubble constant. This is known as Hubble tension. And that is something which slightly hints towards the fact that cosmological constant might not be a fair description of dark energy. And that is something on which our research is still going on. And we are still working on it. I am still working on it personally. There are a lot more models of dark energy, more complex models of non-zero curvature as well. And we are trying to find out which actually represents our universe. And if the dark energy is present, what exactly the dark energy is. Till the time we do not find dark energy, we will not know how the universe is expanding and what will be the future of our universe. So yeah, as someone has said, are there any missing parts in cosmological constant? Yes, it is possible that our cosmological constant is a constant. It is possible that our dark energy might not be a constant at all. It is possible that the W that we saw in dark energy, we are assuming it is a constant for matter and radiation. I mean, it is a constant for matter and radiation. It takes the value of 0 for matter and 1/3 for radiation. But we have also assumed that for dark energy, it takes the value of -1, which is a constant. What if dark energy is formed of something for which W is not constant and it itself varies with time, as someone was saying before? So we have assumed all these stuff. So there are many models currently in work which are removing all these assumptions and trying to fit data to it and trying to find out which better fits the universe. The research is still going on. Any of you guys, if you would have find even a little bit of interest in this session, and if you go on to pursue research in this field, this is something which is very wild. And then once you do that, it is a Nobel winning stuff. when I talked to my guide about this thing, he did mention that it is something which is worth winning Nobel. So yeah, you can move to the last slide about feedback form, and then once you do that, you can like stop the recording. And yeah, to the guys who actually missed the who left beforehand, you guys can fill this feedback form when you see it in the recording. And rest of you, I request you to fill the feedback